This is the second lecture on the heart. I call it Heart 2. And this is going to focus on cardiac muscle contraction and just the rhythm of the heart. It's helpful to look at the cardiac muscles having two different types of cardiac muscle cells. There's the cardiac muscle cells that contract, called contractile cardiac muscle cells. These are the cells that are responsible for the contractions that pump the blood to and from the heart. These cells maintain a stable resting potential, and they're similar to the skeletal muscle cells in that they're stable and they don't contract spontaneously. The second type of cardiac muscle cells are pacemaker cells. These are the cells that coordinate the contractions of the heart cells. These cells have the ability to spontaneously depolarize. In other words, they don't need to be stimulated by a nerve to have an action potential begin. They can spontaneously depolarize on their own. These heart cells are electrically joined together by gap junctions, and these pacemaker cells connect not only to pacemaker cells but also connect to the cardiac contractile muscle cells, so that as a result of them all being connected together, these pacemaker cells can coordinate and initiate contraction of the entire heart muscle cell population. Unlike skeletal muscle, cardiac muscle can depolarize and contract spontaneously without a nervous system stimulation. The coordinated heart muscle contraction is a function of gap junctions and the intrinsic cardiac conduction system. Remember, we said in the first heart lecture that the heart, for it to be efficient in pumping, it needs to pump in a coordinated manner to get the blood to come out in force. If the heart muscle is not coordinated, if each individual muscle cell of the heart contracted on its own time, schedule, and its own rhythm, then you really would have a lot of flow of movement and a lot of flow of blood through the heart. Only by having a coordinated contraction do you have the blood flow that's optimal through the heart. Well, this coordination of cardiac muscle contraction that's what happens as a result of the gap junction and as a result of the intrinsic cardiac conduction system. There's a network of these non-contractile cardiac pacemaker cells that's called the intrinsic cardiac conduction system. They initiate and distribute impulses throughout the heart to produce a coordinated depolarization and contraction of the heart. For comparison, let's look at the skeletal muscle like we did in Anatomy 1. A skeletal muscle, you remember, has a resting membrane potential, and it's stable. It doesn't contract. It doesn't have an action potential in the skeletal muscle until it's triggered by the motor nerve. It has to have motor nerve innervation to start the action potential. Then when it does, it starts to depolarize due to the calcium channels opening and allowing calcium to enter the cell. Eventually the sodium channels close and the calcium channels open, allowing potassium to exit the cells. This is called repolarization. Let me rephrase that, I may have misspoke. Depolarization is due to the sodium channels opening, allowing sodium to enter the muscle cells. Repolarization is when the sodium channels close and potassium channels open, allowing the potassium inside the cells to exit the cells, causing the repolarization. This is what we learned when we studied skeletal muscle contraction. Let's compare that to the pacemaker cardiac cells. Here's an example of a pacemaker cardiac cell. The first thing you notice is that instead of having a resting membrane potential, there's a slope. There's not a resting membrane potential. There's a stable voltage. It's constantly migrating towards a more positive voltage, so it migrates. This is the pacemaker potential. There's a slow depolarization due to both the opening of sodium channels and the closing of potassium channels. Notice that this membrane potential is never a flat line. Looking at the previous slide, the resting membrane potential was a flat line. But in the pacemaker potential, the resting potential is not a flat line, it's a slope line. So The second phase is the depolarization. This is when the action potential actually begins the contraction throughout the cardiac cell. The pacemaker potential reaches threshold, and then the action potential is initiated. Depolarization is due to depolarization is due to calcium influx through calcium channels. Then after depolarization comes repolarization. Then the calcium channels are inactivated and potassium channels open. This allows the potassium to leave the cells, which brings the membrane potential back down to the most negative voltage. And then it starts over again. So these are the three phases to the pacemaker cell action potential. There's the pacemaker potential, there's the depolarization, and the repolarization. Now these pacemaker cells are concentrated in certain areas of the heart. These areas are called the sinoatrial node, the atrioventricular node, the atrioventricular bundle, the right and left bundle branch, and the subendocardial conducting network, or the Purkinje fibers. These areas are where there's high concentrations of these cardiac pacemaker cells. It's helpful to look at these cells functionally as acting like nerves. Even though they're cardiac muscle cells, they really act like nerves in that they conduct impulses similar to nerve cells, and they stimulate contraction to the rest of the cardiac muscles. So even though these are contractile muscle cells, it's kind of easy to consider them something that's functionally similar to nerves. So the pacemaker of the heart is in the SA node, a sinoatrial node. This is where the impulse is initially generated. This is where the heartbeat initiates. The SA node. Then the second place it encounters is the atrioventricular node, which is right here, and this is at the border between the atrium and the ventricle. Then you have the atrioventricular bundle, which connects the atrium and the ventricle. So when this SA node contracts, it causes not only the contraction of these pacemaker cells, but all the nearby cardiac muscle cells are also contracting. So it's going to result in a depolarization of the whole atrium, and it's going to depolarize this whole atrium until it comes down to depolarize in this atrioventricular node, and then it's going to depolarize this area in the septum as it goes down the atrioventricular bundle. Then it splits into these right and left bundle branches to trigger the contraction of the right heart side and also the left heart side simultaneously. And the terminal portion of these conducting pacemaker cells is the subendocardial conducting network. Subendocardial means below the endocardium. This is where the fibers are small and they reach the outlying cardiac muscle cells. So it initiates the contraction of the whole heart as one functional unit. Now these pacemaker potentials can be recorded. There's an EKG or ECG. It means the same thing. It stands for electrocardiogram. It's a recording of the composite of all the action potentials generated by all of the contractile cells at the same time. This is different than what we saw earlier when we saw a single action potential. This is sort of like a tracing of a summation of all of the different action potentials in the heart together, and it's summed up, and it can be recorded from the surface of the body. There's 3 different waves in a normal electrocardiogram. There's a P wave, a QRS complex, and a T wave. The P wave represents the depolarization of the atrium. The QRS complex represents the depolarization of the ventricle, and also the atrial repolarization is in the QRS complex as well. And in the T wave, it represents the repolarization of the ventricular portion. Here's another picture showing the PQRST waves. Again, the P wave represents the depolarization of the atrium. QRS represents the ventricle depolarization, and also the atrial repolarization is kind of hidden in, it's kind of obscured by the large volume of the large amplitude of the ventricular depolarization wave. And then the ventricular repolarization wave is the T wave coming here at the end. We'll look at the different waves separately and we'll look at the sequence of events of the cardiac conduction system. First of all, the SA node is considered the pacemaker of the heart. That's the section of the heart that sets the pace for the heart rate. When that SA node depolarizes, it depolarizes all the cells, cardiac cells, that are touching the SA node, which would include contractile cardiac cells as well as conducting cardiac cells. The conducting cardiac cells is what conducts it on down to the AV node, but the fact that it's connected to the cardiac contractile muscles yields a contraction of the atrium. The atrium contracts starting at the SA node, and it contracts the whole atrium. And this is measured on the surface of the body as a P wave. Then after the atrium is completely depolarized, there's a slight delay. That's the difference between the P and the Q. It's kind of flattened there. There's a slope. It pauses for a moment for the AV node to depolarize. Once the AV node depolarizes, then it sends its stimulation of the contractile cells down the interventricular septum, so that we have depolarization starting in the ventricles. And this depolarization of the ventricles, since this is a large muscle mass compared to the atrium, it's going to show a much larger waveform on the surface of the body at the electrode site. After the ventricles have been depolarized, there's a flat line pause here, and we're waiting for the depolarization of the ventricles to be complete. Then the ventricles repolarize, which is going to result in a positive upward deflection of called a T wave. So T wave represents the repolarization of the ventricle. So then after the T wave the repolarization is complete. So the thing you need to remember on the P waves is to know that the P wave represents atrial depolarization. The QRS wave represents ventricular depolarization plus atrial repolarization, and the T wave represents ventricular repolarization. This slide summarizes the last few slides. You can have damage to the intrinsic conduction system, and that can cause arrhythmias, which are irregular heart rhythms, and a condition called fibrillation, which is a rapid, irregular, uncoordinated atrial and ventral contractions that renders the heart chambers useless for pumping blood. Imagine if the heart cells were all contracting independently without a coordinated effort, it would be useless. It would not be able to pump blood out in a very effective manner. And this is what happens in fibrillation. This is looking at some rhythm strips or some EKG strips. This is normal sinus rhythm. Normal sinus rhythm. You can see the P wave, the QRS wave, and the T wave with each beat. This is the electrical activity. This is not the heartbeat, but the heartbeat actually follows this electrical activity. This is electrical activity that triggers the contraction of the heart, which results in the heartbeat. This is what you detect on the EKG monitor, or when you're under a monitoring process to monitor the heart rate. And this is a regular, normal sinus rhythm. Compare that to this next one. This is atrial fibrillation. Atrial fibrillation is when you have the uncoordinated contraction of the muscle cells. So it's not a concerted effort. This is independently. They contract independently from each other. As a result, there's no P wave. You see these, there's some fluctuation, but there's no real clear P wave in front of the QRS wave. And another thing is, you notice that the QRS waveforms are very irregularly spaced. If they're regularly spaced, it'd be the same distance between each one. But here's a long distance between this one here, this is a short distance here, this is a longer distance, so they're very irregular. That's the characteristic of atrial fibrillation. No P waves and very irregular contractions. Now, ventricular fibrillation is a more serious condition. This could result in actually death, because the ventricular, when it fibrillates, that means that none of the muscle cells in the ventricle are contracting at the same time. So they're kind of contracting on their own without being synchronized. So there's no appreciable flow of blood. The blood kind of just stays in the ventricle and doesn't get pumped out. Since the blood doesn't get pumped out, it doesn't go to the lungs, doesn't go to the brain, so it can be result in very serious medical complications. You've probably all heard of the electrical defibrillator. What does the defibrillator do? How does it work? Basically, it shocks the heart. It shocks the heart so that it basically stops the heart from beating. It stops the electrical activity of the heart. Remember, these pacemaker cells, they can spontaneously start to depolarize and start to contract. Remember, the single action potential of the pacemaker cell have the slope up. Once that slope reaches threshold, it's going to initiate a contraction. Once the contraction initiates in the SA node, then it goes through the conduction system of the heart and naturally resets the heart rhythm of the heart, causing all the cells to start firing at a more natural, normal rate. Look at the cardiac cycle, the mechanical events of the cardiac cycle. If you were to look at a heart during its beating and during the phases of the heart, you see a dramatic writhing movement. It contracts and it relaxes. It contracts and it relaxes. It contracts to empty the blood out of the chambers, then it relaxes to let the blood fill the chambers. These periods of contractions is known as systole. The period of relaxation is known as diastole. And I have here said the mechanical events always follow the electrical events. The electrical events of the EKG is what triggers the muscle to contract. The muscle contraction is what causes the mechanical events of blood flowing through the heart and the valves opening and closing. That's the heart sounds. The heart sounds that you hear when you listen to the heart are the result of the sounds made when the heart valves are opening and closing. So look at the different phases of the cardiac cycle. We'll start with ventricular filling. Now, in ventricular filling, the AV valves, atrioventricular valves, are open, and then 80% of the blood from the atrium just passively flows down to the ventricles. To get the remaining 20% of the blood into the ventricles, to really top off the tank of the ventricles and to get the most blood in the ventricles, the atrium contracts. It contracts because of the SA node, and the contractile cells are causing the atrium to contract, and it squeezes the remaining blood out of the atrium into the ventricles, so the ventricles are now full of blood. This is the mid to late diastole stage. Now we go to ventricular systole, which is when the ventricles contract. Now the atria relax and the ventricles begin to contract. That raises the pressure inside the ventricle, which closes the AV valves. Here's AV valve here. So when this ventricle squeezes down and pressure inside the here increases, it's going to close AV valve so that blood doesn't go back into the atrium. The blood is expelled out through the pulmonary trunk here or out through the aorta in the left side. It forces open the semilunar valves, which open up towards the aortic and the pulmonary trunk valves. And this allows the ventricle to empty. And these valves ensure that the blood is flowing in the correct direction. Then after the ventricles contract, the ventricles relax. Then the blood that's in the aorta and the pulmonary trunk starts to flow backwards into the ventricle, but it stops because the semilunar valves close. So these semilunar valves close, which allows which prohibits the blood from flowing back down into the ventricle, and this ensures that once blood leaves a chamber, it doesn't come back to the same chamber. It goes on to the next area. Cardiac output is defined as the volume of blood pumped by each ventricle in 1 minute. Cardiac output is equal to the heart rate times the stroke volume. The stroke volume is the amount of blood pumped out by the ventricle with each beat. There are factors that change the heart rate and change the contraction strength of the heart. Anything that causes an increase in heart rate is called a positive chronotropic factor. Anything that decreases the heart rate is called a negative chronotropic factor. Think of chrono as time, like a chronograph or a chronometer. It has to do with timekeeping, so it has to do with timing, and think of the heart rate as a timing event. Now, anything that increases the contractile strength of the heart is a positive inotropic factor. Anything that decreases the contractile strength of the heart is a negative inotropic factor. This shows that there are external innervation of the heart, mainly through the autonomic nervous system. You have sympathetic nervous fibers and parasympathetic nervous fibers. The parasympathetic nervous fibers come from the brain stem, the vagus nerve, and because the vagus nerve, it supplies parasympathetic innervation to the heart, which decreases the heart rate and inhibits the heart rate. The sympathetic nervous system increases the heart rate and increases the force of contraction. So the sympathetic nervous system has an effect on the heart. Mainly, it causes the pacemakers to fire more rapidly, and therefore increase the heart rate, and also increases the contractility of the heart and allows it to relax more quickly. It speeds up the pumping of the heart. This is due to the sympathetic nervous system. The parasympathetic nervous system does the opposite. It opposes the sympathetic nervous system, and therefore slows the heart rate down, but it does not have a significant effect on the contractility of the heart. The parasympathetic innervation is primarily through the vagus nerve. That's the term vagal tone, has to do with the influence of the vagus nerve. The final slide is to introduce the terms of tachycardia and bradycardia. Tachycardia is an abnormally fast heart rate, greater than 100 beats per minute. This would be in a resting phase. Certainly if you're exercising, it's normal to have a heart rate over 100 beats per minute, but in a resting, when you're calm and relaxed and resting, if it's over 100 beats per minute, it's considered tachycardia, and that's abnormally fast. Bradycardia is abnormally slow heart rate of less than 60 beats per minute. Again, this is, if you're a very well-trained athlete, you may have a normal heart rate less than 60, but for somebody that's not a highly trained aerobic athlete, if it's less than 60 beats per minute, it's usually something abnormal.